In this video, we'll talk about a famous example of a power series and see how we can use that to do things going forward. We're going to look at this new power series here. It's the sum from 0 to infinity of x to the n over n factorial. What do we know about this power series? Well, the ratio test tells us that our rho should be the limit as n goes to infinity. And after we simplify, absolute value of x over n, which is just 0, which means this always works no matter what x is, so my r here is infinity. So my series converges everywhere. Let's try some other stuff to see if we can see what's going on here. Let's differentiate this function. So f prime of x should be the derivative of this power series, n from 0 to infinity of x to the n over n factorial. I can differentiate because I can do this term by term because my series converges everywhere. This gives me a sum from n equals 1 to infinity, getting rid of the 0 because it's going to be a 0 when I bring down the n, of n times x to the n minus 1 over n factorial. Well, I can cancel the n there from the top and the bottom, which will give me a sum from n equals 1 to infinity of x to the n minus 1 over n minus 1 factorial. And then if I shift my index by setting m to be n minus 1, I will get the sum m equals 0 to infinity of x to the m over m factorial. That's weird. That's f of x back again. We have a function whose derivative equals itself. What do we know of a function that does that? It's the function e to the x. And you can use Taylor series to prove this more directly, but this is the power series expansion for e to the x. So we can use this fact, this is now e to the x. This gives us a power series expansion function that we know, and b, an example one that converges everywhere. And so this is another chunk of examples that we have can be built around using e to the x as a base case for the different examples. Let's do one more example the other way. Find a power series expansion for 1 over x squared minus 4x plus 4. The key thing to realize here, this is 1 over x minus 2 quantity squared. How am I going to get to an x minus something quantity squared? Well, if I take 1 minus u and I differentiate it, this will give me a 1 over 1 minus u squared. The minus sign goes away with the other minus sign from the chain rule. So what does that mean? Well, that means if I look at instead 1 over 2 minus x, this I can figure out how to write as a power series. The point is, once I differentiate this expression here, I will get to something that looks like 1 over 1 minus u squared, which is what I want to see at the end of the day. So this I can rewrite as a 1/2 times 1 over 1 minus x over 2, right? I need to get this coefficient to be a 1 before I can use my formulas. So this tells me this is 1/2 sum n equals 0 to infinity, x over 2 to the n for x over 2 less than 1, or x less than 2 in absolute value. And then I can differentiate. So 1 over 2 minus x squared, which is what I want to see, is the derivative of 1 over 2 minus x. We need to differentiate this power series. 1/2 sum from 0 to infinity of 1/2 to the n x to the n. Well, now I can just differentiate this. I get a 1/2 staying out front. I go in term by term, n equals 1 to infinity. I will bring down the n, 1/2 to the n, x to the n minus 1. And this is valid for absolute value of x less than 2. You could shift this a little bit and write it as something like sum from m equals 0 to infinity of m plus 1, 1/2 to the m plus 2 x to the n if you wanted to, but you don't have to make that change. The answer there is totally fine. This just gives you one more example of a power series, and one that converges to a function you already know and know a lot about, as well as another trick for figuring out power series that you don't know using derivatives of those functions as well.